Okay, well, I want to talk about what has transpired over the last 4 to 5 years in intro chemistry at Harvard. And as Mark mentioned, the subplot here is linking concepts with context. And the question we were trying to address was to develop an innovative university-level strategy leading to a proactive engagement in science and technology with respect to the nation's future. So just so I'm very clear here, we're not explicitly trying to draw more chemistry concentrators in. We are trying to infuse chemistry and the physics that goes along with it into the structure of the evolving chemistry curriculum. And the first question is why? And so it's our very strong belief that we need a new strategic approach to introductory chemistry, and there are many factors that begin to drive toward that need. One, of course, is the physical sciences hold the key to solving problems of immense concern to this generation and to future generations. And of course, the biological, chemical, life sciences community has been at this for 40 years, very, very effectively, solving cancer, HIV, a lot of the societally important problems required the fusion of biology with molecular level chemistry. It's the physical sciences that I think in many ways are culpable. They've been a little bit more, let's say, self-righteous about their intrinsic importance to society, emerging, of course, from the atomic bomb, NMR, radar, and so on. They thought that society owed them support in perpetuity. And of course, that disappeared when the Berlin Wall came down. They had no idea how important the Cold War was to pushing that side. And so now, of course, there are massive and very intriguing problems to solve in delivering energy in a way that's sustainable to 7 billion people, going on to 10 billion by the middle of the century. And by the way, you know, modern humans emerged out of the central part of Africa 160,000 years ago, and I define a modern human as somebody, if you gave them a haircut, toothbrush, put them in a freshman physics or chemistry class, we couldn't tell them apart, and they would do reasonably well on the exams. So, you know, it took 7,000 human generations to reach a global population of 2 billion. And then within one human lifetime, we're going from 2 billion to 10 billion. That is a profound driver on the requirement for energy. And we'll see the numbers here in just a little bit. But actually, a more sensitive function is per capita income. You have to multiply population times per capita income times energy intensity to calculate global energy consumption. And as the evolving, developing nations bring people in from the rural to the urban environment, their energy demands go up dramatically in that single step, and so does their income. So it turns out it's the product of those that matter. So the next issue, of course, is the central role and responsibility that the physical sciences inherit because of their central role in solving these problems. And that is a responsibility, and it simply has to be addressed, and it has to be dealt with. The next issue is this question of the responsibilities that universities have to prepare their graduates. Of course, my institution built its entire backbone on Latin and Greek, and all of a sudden decided one day that wasn't going to cut it for the future. So, of course, the entire structure of blending research and teaching became the central model that emerged into the 20th century. But we're going through a similar dramatic need for transformation now, because when our graduates walk out of a university with their diploma, it's no longer a club that is satisfied, the entry to which is satisfied by a set of specific requirements for courses. They're confronting a very rapidly changing world, and they're confronting international competition that is truly profound. And universities have simply got to step up and recognize that responsibility, because, as we've discovered, if you don't clearly think about what those responsibilities are and reflect them back into the curriculum, and you screw it up in the freshman year, you never recover because you lose those students. And there's a tremendously powerful bifurcation between the physical sciences in the university and the rest of the population, which, by the way, is about 80% of it. And then that propagates forward in time as they go out into society. And yet, this ability to converse and think from the fundamental principles and link that into a larger global context is truly a crucial responsibility. This large departure of undergraduates from the physical sciences is simply straightforward evidence. As I'll talk about, Carl Wieman has been very articulate about this and why, in addition to content, it's important. But Joe Handelsman has also been very effective in monitoring and measuring the degree of incapability of graduating students. And of course, she has this fantastic series of interviews at the University of Wisconsin. She's at Yale now, and she didn't pick, the tails of the distribution. She was looking at the core of Wisconsin graduates, and by the way, visited the state capitol at the same time. We were asking fundamental questions that anybody with a college degree really needs to know, and the results are very concerning. So one aspect of this is that these introductory courses are taught without a compelling context. And not only that, physics and chemistry are separated, which wastes massive amounts of time, of the students' time at the introductory level. And the fact is that the driver in the context of how most of us got into science, and it depends on the era. I mean, speaking for myself, the Cold War was a huge issue. I felt that if I didn't understand physics, I was never going to be part of this Cold War effort. And yet that was a very compelling context. We have to be very careful that the context is built explicitly into the situation. Research has demonstrated how students learn or don't learn chemistry and physics. This is where Carl Wieman has been so profoundly important. I'll mention that in just a moment. And then illiteracy of university graduates in the physical sciences comes back to this now mounting body of evidence. So this and similar concerns led us to create a new course of physical sciences. Now this is in the chemistry department. And I have to say, when I first suggested calling the physical sciences, because you can't really solve a problem without blending physics and chemistry, this is in the chemistry department, by the way. I thought, the physics department was going to be ballistic, that we're moving in on their territory. No problem. They're completely tone deaf to this problem. So physical sciences is now in as a core piece of the chemistry curriculum, but the physics department has just created Physical Sciences 12. So here we go. What drives the strategy behind this course is this responsibility that the university has, but also revolutionary developments at the Union of Chemistry and Physics are really setting unprecedented problems and solving unprecedented problems at the intersection of science and technology. And in particular, I want to focus specifically on, we're coming up on commencement, and those students walk out with a degree. And if the universities haven't looked forward 5, 10, 15, 20 years at what those students are going to confront, and I really enjoyed the sessions in the early part of the afternoon, because all of the message there was that you have to couple these approaches together, including the soft subjects of how you actually deal with people, but a lot of that's coupled to the larger context and the concern and understanding of what those are. So, decisions of what the curriculum is crucial. Getting it correct in the freshman year, and if the separation between science and society occurs in the freshman year, it's really, for that generation, irreversible. So these graduates that are walking out of commencement in the next couple of weeks have to confront this question of what technical forces are shaping the modern world. It doesn't matter if they're going into law, business, economics, international political negotiations, politics, whatever. They have to have a sense of where these technical forces are and how they're shaping the world. The second point is the frontiers of innovation and what implications they have for advancing professional endeavors. Now, historically, it's been in science and technology, but that's no longer the case. You can't do an econometric calculation anymore without understanding the intricacies of how energy and energy consequences play into that issue. Government, public health, law, and education all require this interstitial insertion of the understanding of the physical sciences. The next issue is what public policy strategies are founded on solid scientific and technical foundations. And all you have to do is watch a presidential primary debate to be stunned, to listen to the garbage that flies back and forth. And the journalists have a big part to play in this. The journalists don't call the candidates on things that are just demonstrably wrong. And that's why I mentioned earlier in the day that if we don't develop graduates who know how to vote, we don't blame the politicians. In fact, I got into this because I woke up one morning realizing that I was part of the problem because I was carefully teaching freshman chemistry, but I realized I was teaching it isolated from its real impact on the larger picture. And both Ralph and I went through the ozone wars together. We realized how important fundamental science was to the execution of international public policy. And the same is true today, except it's a far larger and far more complex issue. But until we are educating those 2 million students that graduate each year, and by the way, each of them have 2 parents, that's 6 million people a year. Over 10 years, that's 60 million people. That starts to shift the ability of this country to make fundamental decisions that are wise and thoughtful. And I have to say, I really don't think the United States stands up in the world spectrum of understanding the relationship between science and public policy. It's a little bit like gun legislation. 90% of the people in this country want gun legislation, but we couldn't possibly execute it. Okay, so then this growing compendium of research has shown that university graduates are remarkably lacking in this fundamental knowledge. The colors are just terrible here. So research, we have significant, this isolation of chemistry and physics is fundamental to this failure, and the courses that are taught set up this exclusive rather than inclusive picture. That is, if you and I are sitting in a freshman course together and you're working a thermodynamics problem faster than I am, if this is a race along one axis of scientific talent, I'm going to look at you and say, you're clearly going to be a better scientist. I'd better go off and do something else like government. So I leave. But if it's taught in the larger context, there's a very powerful inclusive message, because you might be better at science than I am, but maybe I can argue a case in front of the Supreme Court more effectively. Maybe I can create a new product. And so now I have a multidimensional picture in front of me where I can compete in different directions and in different ways. And of course, the fundamental premise in many ways of freshman physics and chemistry I'll get to in just a moment. So what are the responsibilities when we look forward in time? The primary responsibility is to link developments, structure and function that these physical sciences teach us into this global context. There's one other really key piece, and this comes from E.O. Wilson. He says, if I learned anything in my 41 years, it's the best way to transmit knowledge and stimulate thought is to teach from the top down. Begin by posing large problems, questions, and concepts of the highest significance, and then peel off the layers of causality. So he says, do not teach from the bottom up. Now, this actually sets off a lot of physicists and chemists. So they say, we've got to start with the fundamentals, and we've got to build outward. If you don't handle vector calculus and thermodynamics just right in the beginning, you can go off and do something else. Well, I think, again, the life sciences, the biological sciences have very clearly demonstrated how important this is and how compelling it is in the creation of college curricula. So what do I mean by context? Well, what I mean by context, and the whole point here is to link these central concepts of quantum mechanics, thermodynamics, kinetics, acid base, and so on, into this larger picture. So involved in this context are innovative new materials, nanostructures, technology, leadership. As I'll point out in just a minute, electrochemistry has been completely reborn by the fact that the transportation system globally has to be electrified. National security, independence, primary energy generation, rapid growth in per capita income and power demand, international negotiations. Is Iran building a nuclear weapon out of uranium or out of plutonium? What about North Korea? Can we read the newspaper and deduce that? The answer is yes. The connection between physical chemistry, optical imaging, and human health. This is the attack on a cell of individual viruses that can now be photographed by the union of these two. Then we come to energy production, storage, and distribution. I'll point out in a minute. We receive 10,000 times as much energy per unit time from the sun that all of humanity uses. And then there are feedbacks in this climate structure. These methane clathrates contain 3 times as much chemical energy as all petroleum, coal, and natural gas combined. They're ubiquitous, and they're extremely sensitive to temperature change. And so these larger contextual pictures really drive it. So this union of science and society places this responsibility on the physical sciences because you cannot understand technology leadership, human advances in health, national security, world energy sources, and all of these other contextual parts until you can link that back to the fundamentals of thermodynamics, entropy, acid-base reactions, quantum mechanics, structures, materials, and so on. And it's really the issue of what is this higher education dynamic, and I contend that in every universities are very different. As we pointed out, Caltech and MIT and so on are somewhat different, but largely across the country we start with a reasonably high percentage of students in the freshman courses, and the attrition is dramatic. And the separation, this alienation after the freshman year, to many people, it's just fine. I mean, all we need to do is deliver 10% of these students into grad schools, medical schools, and society is perfectly well off. And that was true, certainly for a few decades after the Second World War. But this zone of scientific and technical illiteracy has now become, I think, the fundamental problem that we have to deal with because of these issues of national security and competitive economic considerations on a global scale, not just from the single internal competition of the United States. So here's an example of some numbers that are extremely important. If on the ordinate we plot the volume of Arctic ice in thousands of cubic kilometers from 4 to 18 against time, this is 1980 to the present, this loss of Arctic ice, the volume that's lost, is so rapid and so shocking that in 2007, when the last international analysis of this was done, it was forecast that this floating Arctic ice would last to the end of the century. We now know that it's not going to last for 5 more years. And this is a problem that differentiates heat from temperature. The most degenerate quantity that you could cite for changes in the global structure is temperature. The reason for that is that oceans have massive heat capacity, and they cover 70% of the globe. The ice systems will never change temperature until the last shred of ice has disappeared. But we can do a thermodynamic calculation about the heat required to go in to melt this. This is great. This is simple first law of thermodynamics. It turns out when you work through this set of numbers, which is simply the heat of fusion times the mass of the ice, you can calculate the energy required per year, and we use kilowatt hours for macroscopic, so 3.6 10 to the 6 joules per kilowatt hour. But the key thing is that the amount of infrared radiation cycling between the Earth's surface and the cloud water vapor structure is 40,000 times the energy per per unit time required to melt the system. So all you need is a slight amount of leakage northward, and you've taken out the cryosphere. And one of the stories I like to tell is that I was testifying in front of a Senate subcommittee, and I said it was all right if I use exponents. And they said, these are senators. I said, okay, 10 to the 18 is a million trillion. Is that all right? He said, that's fine. You know, $1 million that's a campaign. $1 trillion, that's the military budget. No problem. And I said, but remember, you have to multiply those two together. So 3 weeks later, I'm over in China testifying in front of a number of higher level Chinese bureaucrats, and I asked the same question, and there was kind of this deathly silence, and they looked at me and said, do you think we've flown you 6,000 miles to insult our intelligence? And I said, okay, fine, exponents it'll be. No problem. And that was a shocking thing, that the upper level of the Chinese government is incredibly astute, technically. They were insulted when I asked this question. Okay, so now the question that we have to address is, how do we drive the scientific and technical literacy into a major fraction of the graduating class? And that's really where the genesis of the need and the understanding for completely revamping the freshman chemistry has come from. And the current strategy, of course, is to present lectures, text material, and problem sets. Of course, Carl Wyman, we all know, has done so much along a completely orthogonal axis to ask, how do students actually understand freshman physics and freshman chemistry? And his very clear research has showed that the formalism first approach, where they're submitted to the fire hose of the core technology and formalism before they can connect it into a larger contextual, that has serious problems, because the human brain, of which sounds like the battery's going dead. Oh, no. Okay, so Carl's point was that the human mind stores this formalism as memorized material in a part of the brain which can't be accessed when it comes to critical thinking and analysis. So unless you're driving the basic ideas with a larger, compelling context to solve, and you're solving a problem at the same time you're learning it, it's essentially lost. And so this is a key part. So the question is, how do we develop a strategy that weaves this perspective into a proactive role technology? And the key piece of the structure of this course is to tie this contextual axis into the concepts so that they're brought out and they're blended together in a way that connects thermodynamics, quantum mechanics, electrochemistry, and so on into these larger problems that are required to solve. So what I'm going to turn to now and finish up with is how we actually do that. And I'm just going to pick a particular chapter, and since I've destroyed my wife's life for the last 4 years, I have to show you that we came to the conclusion, that is, those of us working on this course came to the conclusion that we needed to write the text, because if this isn't seamlessly woven together, it doesn't function properly. That was one of the first things we learned. But electrochemistry is a great example, because it's the union of Gibbs free energy, electron flow, and chemical transformation. But more than that, it's crucial to the future of this country. And of course, this is the Tesla Roadster. And one of the key pieces here is that we developed Gibbs free energy early on. And by the way, this course, I should have mentioned, is the higher level freshman course. It's got a considerable amount of mathematics in it. And so students opt into it by choosing the harder course rather than the easier course. And we can talk about the conundrum between the larger contextual issues and the difficulty of the core materials. But electrochemistry is a perfect example where when you plot an electrochemical cell, the battle over electrons between the relevant cations, if you plot this on a free energy surface, it becomes very clear how electrons roll down this free energy surface. But more than that, it allows the combination of equilibrium chemistry, Gibbs free energy, and the relationship to cell voltage. And when 4 to 5 of these chapters are based on the free energy surface, everything is put on a free energy surface. So by the end of that block, they're very conversant with free energy. We see it in terms of spontaneity and how it applies to the larger problem set. So just picking out, this is the Tesla Model S, and one of the great clips is to show a Tesla Model S racing to 100 miles an hour against a BMW M5 that has 500 horsepower. Then you see the Tesla Model S blow away that 500 horsepower internal combustion car and say, okay, what about the energy required to propel a car 100 kilometers? And if you look at a standard automobile, it's about 125 kilowatt hours per 100 kilometers. An SUV sitting in reasonable traffic, 250 kilowatt hours. A Tesla Model S is 15 kilowatt hours. And, of course, then you can couple electromagnetism in with electrochemistry, and Michael Faraday was the creator of both, and the idea of cutting Michael Faraday right down the middle, giving electrochemistry to chemistry and electromagnetic induction to physics, I can just imagine his face if he saw what that was. And you can calculate just very quickly what the magnetic field is within the electric motor in that system. And so coupling together the voltage applied to this against the change in free energy per unit time, which is the acceleration, allows you to come right back and calculate the magnetic field. Now, there are some other very interesting numbers that come very quickly out of this. One is that if you calculate what you spend on gasoline for this SUV in traffic, that's about $5,000 a year. A typical car at 20 miles per gallon is $2,500 per year. The Tesla Model S at 10 cents a kilowatt hour is $300 to drive that for a year. But let's convert that to the U.S. population. It turns out that we spend $600 billion a year on gasoline. If we bought electricity, that would be 72. We're talking about over $500 billion differential. And then you say, well, how much was involved in the fiscal cliff? What's the fiscal cliff? It's $100 billion, a fifth of that. What's the military budget? $1 trillion a year. What does the rest of the world spend on the military combined? $500 billion. The DOD got some connection in here? I know what it is. Wrong pocket. Sorry. Okay. So anyway, the whole point is, and Carl Lyman actually was very important in this. When I was constructing the text, I decided, because of the importance of driving home this larger contextual part, the framework of every chapter starts out by setting this larger context. And that's a key part. But the other aspect is that the core of the presentations, of course, involves the essential concepts of quantum mechanics, thermodynamics, but it's the case studies that link these central ideas into this larger picture of building a technology backbone, building a global energy backbone, and building quantitative reasoning, because these are all large problems that have to be broken down into their parts, analyzed, and then reassembled. So these case studies, in many ways, are the defining characteristic and the difference. And so part of the course involves going through these global calculations, where I summarize a couple of months of these contextual global parts, and I go through the calculations and put all of them together, and I see how all of these pieces play together. And just to finish up, this is a piece I like to use, and part of the course is 50 questions that anybody graduating from the university and stepping up to take their diploma should be able to answer with a straight face. So, what's the ratio of power received from the sun to power consumed by human endeavor? That I've already answered. That's 10,000 to 1. What's the amount spent on energy extraction and distribution worldwide? That's $8 trillion. That dwarfs any other endeavor. How do you calculate global energy demand? We've already learned how to do that. Population times per capita income times energy intensity. How do you calculate the increase? You do that by simply putting in 10 billion people instead of 7, and the average income in 2040 will be probably around $8,000 per person. It's $5,000 today. And you can very quickly calculate that. And to meet that demand, how many 600 megawatt power plants do we need to build between now and 2050? Is it one a week, one every day, 2 every day? It turns out it's 2 every day. That's the scale of the spin-up of global energy consumption. And if we trace the flow of energy from production to demand, why do we waste 60 to 65% of the energy? And of course, this is the Lawrence Livermore energy flow for the United States. This is in quads, which is quadrillion BTUs. Quad, the only redeeming value of the quad is that the United States uses about 100 of it, so you convert the percentage. Otherwise, it ought to be illegal along with BTUs. But look, when you look at the flow, 60% of the primary energy is dumped, it's wasted, and that's, of course, a lot of that comes out of the flow of petroleum and coal. Look at petroleum pumps 25 units into transportation, and only 6.7 of those units actually go to motive force in driving transportation, and that's, of course, why the electric car is so profoundly important. Next set of how much does the nation spend on petroleum imports? That's $400 billion a year. What fraction comes from the Middle East? Only 10%. That's a very important number when we're thinking about strategy. How you calculate the energy to drive a gasoline car 100 kilometers, an electric car. How much does the nation spend on gasoline? We've already done that calculation. Another profoundly important thermodynamic lesson is if we heat our home by burning natural gas in the basement, and we extract 95% of that as heat, is it better to do that or put that natural gas into an electric power plant, deliver the electricity to the house, and use that with a heat pump to heat the house? Well, this is a crucial lesson in energy per unit molecule. 3 halves kT. Turns out that you can go from 273 Kelvin to 293 Kelvin with a tiny amount of work. So you can achieve 300 to 400% efficiency against directly burning that fuel in the house. Very crucial. Okay, I'm going to finish up. Am I out of time? More or less. Okay, less. Okay. We use 3 terawatts of power. If we generate a third of that in Arizona from concentrated solar thermal, what's the area of Arizona? What fraction is required? About 8%. What about another third of our power from wind? That's about 15% of the area of the Middle West, which also can co-raise food. This is the final point here. This is this issue of the loss of Arctic ice. And this loss of Arctic ice is profoundly important because when that ice is gone, it dramatically changes the temperature gradient between mid-latitudes and the poles. When you flatten that temperature gradient, you relax the overturning structure of the Earth's atmosphere. And you know from the last time the Earth had 500-600 ppm of CO2 that there was no temperature difference between the equator and the pole because the infrared radiation field fed through water in the stratosphere to heat high latitude. And so the fundamental structure of the current climate is set entirely by the fact that we have very cold polar regions, very warm, very hot tropics. And when we destroy that temperature difference, we're not talking about minor changes. We're talking about fundamental changes and how important thermodynamics is to looking at that. So I'll just end up by saying that the current and I think catastrophic separation of the sciences from the larger picture of the structure of university education needs to be replaced by combining not only physics and chemistry in combination, but those sciences have to play directly into the way in which that educational process moves forward to prepare those students for graduation. Thank you very much.